Okay, in this video we are continuing Chapter 16. In the last video we looked at steel beam design, and in this video we're going to look at timber design. And there is a pretty significant difference between the two. That's due to the fact that steel and timber are very different materials. They behave in very different ways. One of the characteristics of wood that makes it very different from steel is that it is anisotropic, which basically means it behaves differently in different directions. So let's say we've got a piece of wood here. Wood is made up of grains, or its cells have a granular kind of texture to them. All running in one direction. So along the length of a piece of timber, you've got wood grain running in that direction. These bundles of fibers, these grains running in that direction, give it a great deal of strength in that direction. But if we look at one of the ends of it, it's basically a bunch of well, the analogy I've heard used is think of grains of wood as a bundle of drinking straws. Okay, all running in this direction. It's strong in compression in this way. It's strong in tension. But if we were to compress it in the opposite direction, perpendicular to those grains, it would be very weak. Imagine pressing down on a bundle of drinking straws. It would smash vertically quite easily, whereas in the direction of the straws themselves, it would be quite strong. So because of that, there are lots of different allowable stresses. If you look up in appendix, let me check that, I think it's appendix F, you'll see a variety of different allowable stresses for timber. You'll see FC, which is the allowable stress in compression, parallel to the grain, so that would be like in this direction. You've got FCP, compression perpendicular to the grain. And then you've got tension, the allowable stress in tension. Again, that would be parallel to the grain, so that would be like in this direction, but in tension rather than in compression. FB is bending. So if you'll recall, bending is sort of a combination. If I draw a beam from the side, give it some height here, simply supported beam with a pin and roller connection, bending stresses are a combination of compression stresses in the top with tensile stresses in the bottom. And that's all going to be perpendicular. Those two reactions, or those two forces, the tension and the compression, are parallel to the wood grains. Wood is laid down on its side when it's used as a beam, and so that grain runs left to right. And both of these directions are also running left to right. So wood is strong against bending because the stresses are parallel to its grain, not perpendicular. And then the last one we'll have to check, which is perpendicular to the grains, is the allowable shear stress in a beam. So depending on the species of wood, in our appendix F we have Douglas fir, southern pine, hem fir, eastern white pine, redwood. They all have different allowable stresses. So we'll have to check the appendix F, depending on what species of wood we're dealing with, for allowable stresses, and also the modulus of elasticity, E, varies depending on the species of wood. It looks like that's anywhere from 1100, not 11,000, 1100. Let me undo that. There we go. 1100 KSI and that looks like Eastern White Pine has the lowest value, up to 1700 KSI. Like Douglas Fir is one of the ones with the highest modulus of elasticity. The other thing that makes wood quite a bit different than steel is in steel we use the plastic section modulus, and the reason for that is that when the stresses in the top fiber and the bottom fiber get to the yield stress in steel, you've still got all this material in the middle that hasn't failed yet. So you can keep loading it, keep loading it, keep loading it until it fails all the way from top to bottom. Wood is not as predictable as steel. Wood is a naturally occurring product. It's not man-made. There are all sorts of natural defects. And so essentially we have to be more conservative with our design when it comes to wood. Once we get to the point here where the stress in the top or the bottom of the beam reaches that allowable bending stress, we're going to stop. We're immediately going to stop loading it and say that's enough. We've reached the allowable point. It would be unsafe to exceed that load to cause any additional moment or any additional stress. So in wood, we do not use the plastic section modulus. We use the elastic section modulus in order to determine when the stress in the outer fiber reaches the allowable point. So we learned earlier that bending stress is equal to moment divided by section modulus. And so when we start designing a wood beam, the first thing we're going to do is try to choose a beam with an adequate section modulus, this time elastic section modulus. And that section modulus will be equal to the moment that is applied to it by whatever the load happens to be, divided by that allowable stress. That will give us a section modulus, which we can then turn to the appendix and look for the appropriate size timber that will give us adequate strength. Okay, let's go ahead and take a look at an example problem. Okay, so if we look at example 16-3, in this example we have a pretty common application of wood beams, and that is floor joists. Joists are basically just a repetitive system of beams. So we have these joists that are supporting a floor. The joists are spaced at 16 inches on center. So the spacing between any pair of joists is 16 inches. So 16 inches from the left one to the center one, and from the center one to the right one, also 16 inches. And the load applied to the floor is spread out in pounds per square foot. We have two different types of load here. We have a live load of 40 pounds per square foot, and we have a dead load of 15 pounds per square foot. So what is live load and what is dead load? Live load is basically transient loads, things that move, things that are sometimes there, sometimes not. So the people inside a building, the furniture, anything else that moves around and is not always present is considered live load. Dead load is a permanent load. It's part of the structure itself typically. So the floor itself, the joists themselves, the walls, the ceiling, all the parts of the structure itself contribute to dead load. So this load gets spread out over the floor in two directions. It's a two-dimensional load. It's pounds per square foot, but we're just kind of looking at it in a cross-section here. But what happens is, and I'll kind of change the color of my pen here to illustrate it. This load that gets spread out amongst all these joists, if we cut it in half right here, half of the load goes to this joist, the other half load goes to the other. And then again, if we split right down in between the spacing between those two joists, half of the load goes to the right and half of it goes to the left. So one joist ends up collecting the load in a strip that is equal in width to the spacing of the joists themselves. So in other words, this is 8 inches worth of load, this is 8 inches worth of load, so together it collects 16 inches. Well, that's the same as our spacing was. So this 16-inch width here, this is called the tributary width. And it happens to be equal to the span of the joists. And it's basically just saying how wide is the strip of floor that contributes load to this particular joist. Okay, so in order to find the load on this joist, we would need to multiply these pound per square foot loads by the tributary width. So 16 inches converted to feet, there's 1 foot for every 12 inches. And so we convert that, and 16 inches is 1.333 feet. So if I take 40 pounds per square foot times 1.333 feet, that will give me 40 times 53.3 pounds per, not square foot now, but just pounds per foot, or pounds per linear foot. And if I take the 15 pounds per square foot multiplied by 1.333 feet, that is going to be equal to 20 pounds per linear foot. So we're used to looking at a beam from the side, simply supported beam with a uniformly distributed load, which due to the floor loading in this problem and the tributary width will be, I'll keep it separate for now. W is going to equal a live load of 53.3 pounds per foot and a dead load of 20 pounds per foot. So this is actually a pretty good place for us to stop. I'm coming up pretty close on my 15-minute limit for this video. So we've established the load. We'll continue this example problem in the next video.